This is our second video on the technique of contrapositive proof. Recall that the contrapositive of P implies Q is the negation of Q implies the negation of P. So in other words, our contrapositive is the negation of Q or not Q implies not P. And this is logically equivalent to P implies Q, the contrapositive. So let's do another example. Let's prove that if xy is odd, then x and y are both odd. Note that contrapositive proof is a good technique to use in such a problem because, again, if we start with a direct proof, if we tried to do this directly, then we would start with xy is odd, so xy is equal to 2k plus 1 for some integer k. And so what then could we say about x and y? You know, if we divide both sides of that equation by y, for example, we don't really even know where we are, is x, so this would be hard to prove directly, and we'll instead use the contrapositive proof technique. So first of all, our first question should be, what is the contrapositive of this statement? So what is the contrapositive of this statement? Obviously, it should be the negation of Q implies the negation of P. But let's write that out in words and show exactly what we'd be trying to prove with the contrapositive. So actually just pause the video for a moment and take a second to write out what the contrapositive of this is in words. So the contrapositive of this statement is not x and y are both odd implies not x, y is odd. Let's translate that. Let's simplify that. So the negation of x and y are both odd is x is not odd or y is not odd. So remember by De Morgan's law that the negation of s and t is not s or not t. So that's De Morgan's law. So that's the negation of q implies the negation of p. If xy is not odd, then xy is even. So to make it even a little bit more clear, x is not odd or y is not odd. Well, if x is an integer, we assume, and it is not odd, then our contrapositive would be x is even or y is even implies xy is even. Okay, so that is now what we're trying to prove, and we are saying that this statement is logically equivalent to this statement because it is the contrapositive of that statement. So try to prove that statement, and we'll talk about that in just a moment. Okay, so let's do this proof using the contrapositive technique. As we saw above, the negation of the statement Q is the negation of x and y are both odd. If it's not true that x is odd and y is odd, then it's the case that x is not odd or y is not odd, or in other words, x is even or y is even. So to do this proof by contrapositive, we are first going to assume the negation of Q. So suppose that x is even or y is even. We are assuming that that is the case. Now we could at this point do cases. We could do the case that x is even or the case, as well as the case that y is even. But these cases would be essentially identical besides the assignment of x and y. So this is a situation where instead of using cases, we can say, without loss of generality, assume that x is even. So it could be that x is even, it could be that y is even, it could be that both are even. But if all we're assuming is at least one of them is even, then we can, without loss of generality, assume that one of the two, and it doesn't matter which one, is even. It's just the variable name. So since x is even, that means that x is equal to 2k for some integer k. And let's think about what we're trying to prove. We're trying to prove the negation of p. The negation of p is xy is not odd, or in other words, xy is even. So we're trying to prove something about xy. That means that we should look at that product. So let's consider x times y, which we now know by substitution to be equal to 2k times y. So that's 2ky, where k times y is an integer, and therefore x times y is even. So we have completed our proof. We've shown that the negation of q implies the negation of p. If we wish, we could make that clear to the reader and say that we have shown that the negation of x and y are both odd implies the negation of xy is odd, and therefore the initial statement is true by contrapositive. And we have finished our proof. Okay, let's look at another proof using the contrapositive technique. Let x, a, and b be integers. If x does not divide the sum a plus b, then x does not divide a, or x does not divide b. So in symbols, x does not divide a plus b implies x does not divide a, or x does not divide b. So that is what we are trying to prove. Recall just the definition. A divides b if b is equal to a times c for some integer c. So that's the definition of divides. So first, be careful about figuring out, we want to find contrapositive of the initial proof statement. So find the contrapositive of that statement and then try to prove it. So give that a try and pause the video and we'll talk about it in a moment. Okay, so let's take a look at this proof. Let x, a, and b be integers. If x does not divide the sum of a plus b, then x does not divide a, or x does not divide b. So on our piece of scratch paper on the side, let's try to find the contrapositive of the initial statement. Find the contrapositive of the statement x does not divide a plus b implies x does not divide a, or x does not divide b. So we're trying to find the contrapositive of that entire statement. So our contrapositive would be the negation of q, the negation of x does not divide a, or x does not divide b, implies the negation of p, the negation of x does not divide a plus b. So now let's unravel that. So the negation of x does not divide A or x does not divide B is, again, using De Morgan's law. It is not true that x does not divide A, and it is not true that x does not divide B. So that's using De Morgan's law. It flips the ors to ands and vice versa. Implies negation of x does not divide A plus B. Well, if it is not true that x does not divide A plus B, then x does divide A plus B. And let's just continue making that as simple as possible. The negation of x does not divide A is, of course, x does divide A, and x does divide B implies x does divide A plus B. So this is the contrapositive, and this is what we are trying to show. So we are trying to show that. So proof by contrapositive. So suppose not Q, in other words, suppose that x does divide A and x does divide B. Then what is the definition of that? Then A is equal to x times C for some C in the integers, and B is equal to x times K for some integer K. Note that we need to use two different variables, C and K, because we don't want to use the same variable. That would indicate that A and B were actually the same integer. Okay, so what are we trying to prove? We're trying to prove something about x dividing A plus B. If we're trying to prove that x divides A plus B, let's just remember the definition there. We are then trying to show that we want to show, this is on our scratch paper, A plus B is equal to x times some other integer j. So we want to show that on our scratch paper. That's helpful. So we're trying to show something about A plus B. That means let's observe that A plus B is then equal to x times C plus x times K. And can we show that A plus B is equal to x times some integer? Yes, we can factor an x out. So observe that that is then equal to x times C plus K, where C plus K is an integer, and therefore it is the case that x divides A plus B. So we have shown that. And now we could wrap it up. We could finish there if we're pretty sure that our reader is very aware of contrapositive proof. We could just end our proof at that point, or you could choose to spell it out a little bit more and say that since x divides A and x divides B implies x divides A plus B, the contrapositive holds. So x does not divide A plus B implies x does not divide A, or x does not divide B, the negation of the original of Q. And now we are done. Okay, so let's do another proof, this time about real numbers instead of integers. So we are trying to prove that if x is a real number, then x cubed minus x being greater than 0 implies that x is greater than -1. So think about what is the contrapositive of that statement and then try to prove it. Okay, so let's try to prove this. First, observe that a direct proof would be difficult because if x cubed minus x is greater than 0, it's sort of hard to see where to go from there. So let's first find the contrapositive of this statement. So that's the negation of Q. In other words, if x is not greater than -1, then x is less than or equal to -1. That's the full negation of x being greater than -1, implies the negation of p. And so the negation of p is x cubed minus x is less than or equal to 0. Don't forget the or equal to part. So we can see that our proof is going to start by assuming that x is less than or equal to -1, but then it's not totally clear how to get this x cubed minus x is less than or equal to 0. Let's start to think about how we might approach that. So we want to show x cubed minus x is less than or equal to 0, and again, we're still on the scratch paper side of the proof. We're not actually writing out clear logical steps yet. So we want to show that x cubed minus x is less than or equal to 0. Well, that's equivalent to showing that x cubed is less than or equal to x. And so how could I show that? One thing I could do is, if the only thing I know is that x is less than or equal to -1, I could start to break apart that x cubed, knowing that x is less than or equal to -1. So x cubed, what is that? Well, it's x squared times x. And now I can give an inequality that's less than or equal to x squared times -1. If you multiply something by something less than it, then you'll get a lesser product. And so that would be equal to x squared, or to negative x squared. And we could further break that down. So that's negative x times x. And we could continue breaking that down, just knowing the one thing we know, that x is less than or equal to -1. So this is less than or equal to negative x times -1. And negative x times -1 is just plain x. So what have we shown? We have shown that x cubed is less than or equal to x, which would tell us that x cubed minus x is less than or equal to 0. Okay, so that was some scratch work on the side, and you might have had to play around with some algebra for a while before you came to that conclusion. But in any case, now we've sort of thought about it on the side, how will this proof go? And so now we can actually do our proof as a step-by-step argument. So proof by contrapositive. Suppose that it's the case that, not Q, x is less than or equal to -1. Then we can consider x cubed and observe that x cubed is equal to x squared times x, which is less than or equal to x squared times -1, since x is less than or equal to -1. And so x cubed is less than or equal to negative x squared, which is equal to negative x times x, which is again less than or equal to negative x times -1, which is equal to x. Therefore, x cubed is less than or equal to x implies x cubed minus x is less than or equal to 0. So x less than or equal to -1 implies that x cubed minus x is less than or equal to 0. And by contrapositive, x cubed minus x greater than 0 implies x greater than -1. And we are done. Okay, let's do one more proof in this video. Let x be a real number. If x to the 7th minus 5x squared plus 2x is greater than or equal to 0, then x is greater than or equal to 0. So give that a shot. Okay, so let's take a look at doing this proof. So as scratch work on the side, let's find the contrapositive of this statement. And the contrapositive of this statement is not Q. So x less than 0 implies not P. So x to the 7th minus 5x squared plus 2x less than 0. So that is what we are trying to prove. Let's just continue on the scratch work part before we start the formal proof. So if we are assuming that x is less than 0, then what do we know about x to the 7th? So we have a negative number to an odd power, and we know that that is going to be less than 0. If we look at x squared, that's going to be greater than 0. It's a negative number to an even power, but negative 5x squared will be less than 0, negative times that. And 2x, 2 times the negative number, will also be less than 0. So when you add those negative quantities together, x to the 7th minus 5x squared plus 2x will be less than 0. Okay. So that's how our proof works. So now let's write it up. Let's say proof by contrapositive. Suppose that x is less than 0. And we can now observe that a negative value to an odd power is negative, to an even power is positive. So x to the 7th is less than 0, and 2x is less than 0. Note that x squared is greater than 0, so negative 5x squared will be less than 0. And so what have we got? So x to the 7th minus 5x squared plus 2x is all together going to be less than 0. And we have shown the contrapositive of the proposition. So we are done, and that's it.